Thank you. Good morning, everyone. So my name is Hassan Takabi. I'm an assistant professor at the University of North Texas. So the work today I'm going to talk about is privacy preserving machine learning as a service, as a joint work with my PhD student Hassan Takabi, and in collaboration with is it good? Mehdi Qasemi from University of Saskatchewan, Canada, and Rebecca Wright from Rutgers. I don't need to tell the audience here about machine learning, so I'll jump right in about why machine learning as a service and why privacy issues here. So as the machine learning services has grown in different domains, nowadays, similar to any other cloud service, we could have machine learning as a service, which essentially we can train machine learning models on a cloud infrastructure, and also once the model is built, use that for prediction or classification of the data that we have. There are several such services currently available from big companies, and there are a lot of startups in this domain: Microsoft Azure, Amazon, Google, GraphLab, and there are several other companies that are providing this service. But of course, when we're dealing with machine learning, we're dealing with data, and privacy-sensitive data is always an issue. So our goal in this talk in this paper is to provide a privacy-preserving machine learning as a service, which allows different parties in the ecosystem to receive or provide services without having to reveal their sensitive data. And essentially, the core contribution is applying neural networks over encrypted data. So that's what I'm going to be talking about. So the threat model that we're considering is that the client has the data, wants to use the cloud service to train a model, but without sharing the data with the service provider. So the data would be encrypted, provided to the service, the model is built on it, and then this client is the only one who will be able to use that specific model built for using its own data. And also, sometimes the servers, the service providers, they spend a lot of resources on building a machine learning model, and they don't necessarily want the clients to know their model. So the privacy of model also is another aspect that should be preserved against the clients. So the solution that we have here is essentially based on homomorphic encryption. So the main building blocks of our work is homomorphic encryption and neural networks. Generally, the work that exists in this area are based on either secure multi-party computation, differential privacy, and our work is homomorphic encryption, another work that I'll talk about. So I'll talk about briefly about the neural network, and then talk about our approach, which essentially the main goal is how to approximate functions that are used in neural network to be able to implement them within limitations of homomorphic encryption. Neural network structure, generally we have an input layer, output layer, and a number of hidden layers. And the neurons that we have in the hidden layer, typically they take an input, they compute a weighted sum of input, operate a specific function on the sum, and then output that. So most of the practical homomorphic encryptions that exist usually they can support addition and multiplication. So if you look at the operations that are used in neural network, most of them are, or we can break them down to addition and multiplication with the exception of activation functions. So generally, the different activation functions used in neural network, the more common ones are sigmoid or ReLU. So those are the functions so these functions are not implementable in homomorphic encryption as they are. So essentially, what we're doing there out is how to replace these functions and operations that are not compatible with homomorphic encryption with the compatible versions. And our goal is to approximate these functions using polynomials that then we can implement it. So when it comes to approximation, we can basically approximate the function, let's say sigmoid or ReLU, with a different number of functions, different degrees. So the higher degree that we have in polynomial gives us a closer approximation, a better approximation, but it costs us when we want to implement that over homomorphic encryption. So our goal is to keep the approximation to the lowest degree possible. So basically playing with the trade-off between the degree of the approximation polynomial and the performance of the model. In the paper, we talk about theory of how to basically find the lowest polynomial degree of a function within a certain error range. So I'm not going to talk about details, but here essentially is how we're doing the approximating function. So this is a sigmoid function. The blue is the original function, and then the green and red are two approximation of the function. Similarly for ReLU, the blue is the original function, and then the black one is an approximation that we came. So once we develop this approximation function, now we can generate the approximation functions with this. We started implementing different neural networks on the homomorphic encryption and do some experimenting. So we used a large number of data sets from UC-Irvine machine learning data sets. So I just present a few of the results here. So before I talk about the results, so the main thing that basically once we approximate the function, one thing that we consider an approach, because when we're using homomorphic encryption, there is a noise in the computation, and if you want to use bootstrapping approach, the approaches that use bootstrapping are not practical yet. So we came up with an approach that basically we do a noise reduction when the noise reaches a certain threshold. So ideally, we don't want to have any interaction between client and server. That I'll talk about. That's one of the weaknesses of the secure multi-party computation approaches. But for noise reduction, we allow some limited number of communication. As I'll talk, the number is usually much less compared to the SMC approaches. So these are some of the results that we have for several data sets. So this represents the time that it takes to create the original network, the feed-forward operation, backpropagation. This is the number of communications, and then this is the time that it takes to reduce the noise. And we experimented with different number of hidden layers, so neural networks with hidden layers from 1 to 5. And the time basically it starts anywhere from about 3 minutes to somewhere about 20-25 minutes for this is the time that it takes for training. And so this experiment, we used a batch size of 576, but we also looked at if we use larger batch sizes, the increase in the time is not as significant. So for example, if we increase the batch from 282 to 6,000, which is about like more than 20 times, we can see the noise reduction or the backpropagation feed-forward, the increase is less than 50%. Now, if we look at the classification, our result and the number of communication is much better in classification, of course. So again, we look at the networks, the same networks that we train with different number of hidden layers. Here, if we look at the number of communications, it's much less in a lot of cases, up to 3 hidden layers. We don't need any interaction between client and service. But even for the larger data sets that we need, the communication is at the minimum. So we did the experiment with this data, then we moved to larger data sets that are used more in machine learning community. We looked at MNIST, and we trained the neural network over encrypted MNIST data. These are the results that we have, again, for the feed-forward, backpropagation, the number of communication. So this is the number of interaction and noise reduction. So the times look large, but consider that generally training a machine learning model, even with plain data, takes a lot of time. So over encrypted data, this is not unreasonable. Now, as you mentioned, the other work that exists in the literature is mostly based on secure multi-party computation. There's one work that was done based on homomorphic encryption by Microsoft Research, published in 2016. CryptoNets is the closest to our approach. The main difference is that they only do the classification on the encrypted data. So they essentially build the model on the plain data, then only for classification used the homomorphic encryption. So in order to provide a comparison with that approach, We follow the same procedure. We use the same network that they use, so they have a convolutional neural network with 2 convolutional layers and 2 fully connected layers. They replaced the activation function, which they use sigmoid, with the square function. We used our approach to develop the polynomial approximation. We did use both sigmoid and ReLU as activation function and trained the exact same network. The approximation that we got for ReLU was of the degree 3. For sigmoid is the degree of 2. The accuracy of the model, we were able to achieve 99.15% for the network with ReLU and 99.02% for the network with sigmoid. This was the original functions, original sigmoid and ReLU. And when we replace those with our polynomial approximation, the accuracy drop is very, very low, really. So we dropped from 99.15 to 99.10 for the ReLU, and from 99.02 to 99% for the sigmoid. The best accuracy that CryptoNet they were able to achieve is 98.95%. So one thing you have to have in mind that these numbers look very close, but in machine learning, even a 10% improvement in the accuracy is considered very significant. So they're building a lot of new models to slightly increase the accuracy. So this is still considerable improvement. Another aspect that we looked at is the comparison of the throughput. Our approach significantly outperforms the CryptoNet. So when we did classify with this same batch size of 8,192, our approach can make close to 164,000 prediction per hour. CryptoNet was able to achieve about 52,000 prediction per hour. So that's the homomorphic-based approach. Another approach that we compare closely is based on the secure multi-party computation. This was published in Oakland 2017 by Mahassel and Zhang. So the main advantage that we have, our approach compared to generally SMC-based approaches, is the number of communication, because the SMC approaches, there is a huge number of interaction between the client and server, and we minimize those interactions. So this table shows the huge difference between the number of interactions. So this is the network with 1 hidden layer up to 5 hidden layer here and different batch sizes. If you look at the number of communication for our approach is usually fixed, doesn't change with the batch size, and it's like very low compared to the number of interactions that are needed in the SMC-based approaches. And the largest network that we had with the 5 hidden layer, for example, ours is 640 versus close to 30,000 number of interaction for the SMC. We also looked at the amount of data that is transferred in the interaction. For the smaller networks, for example, network with 2 hidden layer and with the batch size of 512, the data transferred in the SMC-based approach is 12 megabyte, ours is 33, but if the network becomes larger, our approach outperforms the SMC-based approaches. For example, for a 5 hidden layer and the same batch size, ours is 155 megabyte versus 159. And if we also use larger batch sizes, in most cases, our approach basically has a better has a less amount of data transferred in the communication. The accuracy of approach also, we were able to achieve 95.15% using the approximation of ReLU over encrypted data for the MNIST. The approach that they presented was 93.4%. I think I'm going to skip this in the interest of time. So just to sum up, we basically, our main idea here is to develop solutions to apply neural network algorithms over encrypted data. The main, the core of work is to come up with good approximation, polynomial approximations for the activation functions used in the neural network. And we did some experiment and compared the approach with other SMC-based approaches and homomorphic-based approaches, which in most cases our work outperforms those work. So there's a lot more work need to be done. So you have to work on more complex data sets. So MNIST is a good starting point, but there are larger, more complex data sets that need to look at. And another aspect for future work is looking at parallelization techniques or GPU-based implementation of machine learning or homomorphic encryption to increase the performance. And that's it, and I'll be happy to take questions.
Okay, we have 3 minutes for questions. I'll try to get to the mic to you, and please speak your question in the mic so they can hear you online.
Hi, nice talk.
Thank you.
There are a lot of different ways to trade off training time in these algorithms, right? So if you have a fixed amount of time to train your neural network, you could like increase the batch size, or in your case, maybe you could use like a higher degree activation function. Like, have you done any experiments to kind of figure out those trade-offs of say like, all right, I've got like 2 weeks to train this thing, and
yeah, so of course, our goal was to get, so we wanted to get as close as possible to the state of the art. For example, for MNIST in the machine learning community, the state of the art is 99.77%, the best reported result. And we continuously trained our model, and we were able to achieve 99.52%. That's the closest that we got. But of course, if you have, so we call it basically, depending on the number of iterations that you train, you usually start from low accuracy, and then as you continue the training, the accuracy goes up. So it depends. You can have a cutoff point basically to say, this is the acceptable accuracy to me, or this is the amount of time that we have, and we're going to train in this one.
Hi, great talk. I wonder to what degree it can be considered a practical solution, given that MNIST takes about 2 minutes to train on a laptop.
Right. So one thing you have to remember that training, even on plain text, like big networks that the companies use, they train for months.
That's right, but I'm talking about MNIST,
so
which is 2 minutes.
Set, the one that basically reported 2-3 minutes is the small data set on a laptop. So so even on the encrypted data, it took like a few minutes, which is reasonable. For larger data set, as we saw, it probably goes to hours or like weeks. So depending on what you consider practical, or still, I can't claim that this is really practical. There's a lot more. This is just a starting point. Because homomorphic encryption itself is still, there is a lot of work going on the crypto community on improving the performance of homomorphic encryption. So that's one aspect. So there's a need for a lot more work in this area.
Thank you.
Okay, are there any other questions? Yeah.
From the stream, if the model is available to just one party, the one who encrypts the data, or to multiple parties?
If the model is available to?
If the model is available just to one party, the one who encrypts the data, or to multiple parties, and also if can be queried by multiple users.
Yeah, so that's part of our future work. So the current model, because the client that, if you use specific client's data to build the model, so that client is the only one can use the model for classification. But part of our future work is how to train on a distributed data from several clients, then the model would be usable with larger number of clients. But that's much more complex, of course.
Okay, that'll have to be the last question. Let's thank the speaker again.